everyone, and welcome back. Today we're going to talk about something called the second derivative test. This is just another tool for us to help us determine about relative mins and maxes. And you might say, well, I already know how to find relative mins and maxes, and hopefully you do using the first derivative. And we take the first derivative, we find our critical values, and we make a sign chart. So that is an absolutely valid way, and that's the way I would encourage you to continue to find relative mins and maxes. But there are times when we can't use the first derivative to make a sign chart, and we're going to see those cases today. And so that's where the second derivative test comes in. So let's read about it and see what it's all about. It says, first of all, if f prime of c is equal to 0, so if the derivative at a given input is equal to 0, and the second derivative at that same x value is positive, then f of x has a local minimum at x equals c. Okay? If f prime of c is equal to 0, and the second derivative at that same x value is less than 0, then f of x has a local max at x equals c. All right, so that seems kind of confusing, so let's break it down for a second and see what this is all talking about. All right, what does it mean if f prime of c is equal to 0? Well, what would our graph have to look like in order for the derivative to equal 0? And hopefully you're realizing that that means you have a horizontal tangent, that it's flattening out. All right, so how can that happen? Well, there's a few different ways. You could have a graph that kind of looks like this. You could have a graph that looks like this. You could have a graph that looks like this. For each of these, you have a horizontal tangent that is existing, so you have a place where the slope is equal to 0. All right, now that's the first part. The second part here tells me that my second derivative needs to be positive. So if my second derivative is positive, hopefully you are realizing that that means it has to be concave up. So if I look at my three pictures right here, the first one is clearly not, the second one is clearly not, but the third one is. And look at what happens when you have a concave up graph and your first derivative is equal to 0. You end up with a minimum. Okay, all right, let's look for the second example here. It says, now again, you have one of these three scenarios. You either have a graph that looks like this, you have a graph that looks like this, or a graph that looks like this. Any of those would give you a horizontal tangent, okay? But now, this time, our second derivative is negative. And if our second derivative is negative, we should know that our graph is concave down. And so again, we can get rid of this one, and here we could see that when we have a graph that is concave down and our first derivative is equal to 0, we have a local maximum at that value. Okay, so our first example here says let y equal f of x be a function that contains the point 0, 2, and has a slope given by dy dx equals xy minus 3x. Determine whether 0, 2 is a local max or a local min of f of x and justify your answer. Okay, so here's a perfect example of a time when you'd want to use the second derivative test. And why is that? Well, if I am given this point 0, 2, all right, so I'm given my x value, so normally what I would do, so I'm already given my critical value point that I'm testing. So I would put my x value here, and I would go for my f prime and my f, and I'd fill in my sign chart. Well, normally you're filling in just an x value into your first derivative, an x value to the left of your critical value and an x value to the right. Well, look at our derivative here. Our derivative, our slope, is dependent upon x and y. I can't use the sign chart because I do not know my y values. I only know x values to the left and right of 0. Therefore, this is not going to be valid. All right, so this is where I want to use my second derivative test. So the second derivative test tells me two things. I first of all need to make sure that I'm going to have a slope of 0, a first derivative of 0 at this point. So that's my first test. To determine if my slope, if dy dx, is equal to 0 at the point 0, 2. So I'm going to take my slope, which is xy minus 3x, and I'm going to plug in 0, 2 for x and y. So dy dx is equal to 0 times 2 minus 3 times 0. So clearly that gives you a value of 0. So we can be sure that our first derivative, our slope, is equal to 0. All right, so that meets the first criteria. Now, the second criteria says that I have to determine whether or not the second derivative is positive or negative. That's going to help me determine if the graph is concave up or down, therefore having a local max or min. All right, so that means I need to go ahead and find the second derivative. All right, well, how do I do that? I take the derivative of the slope. And so I'm going to do d2y over dx squared. All right, so it looks like I have to use the product rule with xy. So that would be x first times the derivative of y is dy dx plus y times the derivative of x is 1 minus the derivative of 3x is 3. All right, so let's go ahead and fill in what I know now. Okay, so I need to go ahead and substitute in my x and my y values, 0 and 2. And also I need to sub in my dy dx. So I know my x value here is 0. My dy dx, well, I just found that for that point to also be 0. Okay, that was this. So I'm going to put that in for dy dx. So 0 times 0 plus y is 2 minus 3. And so I end up with a second derivative of negative 1. Okay, so we got a value that was negative. This tells us, since our second derivative is negative, this tells us that our function is concave down at that point. And so what does that mean? Well, if I have a function that's concave down and a slope of 0, I would say that this would be a relative maximum. Okay, so we're ready to go ahead and make our conclusion. Okay, so we could conclude that the point 0, 2 is a relative max. And our justification is that f prime of 0 was equal to 0 and f double prime of 0 was less than 0. Okay, number 2 says, consider the curve given by x squared plus 4y squared is equal to 12 plus 2xy. Find all points where f of x has a horizontal tangent line. Okay, so it's been a long time since we've done one of these questions, so this is a great question to review, something that we haven't touched in a little bit. So finding a horizontal tangent line. What is that all about? Well, let's review. Horizontal tangent line would of course mean that my slope was equal to 0. So I need to take the derivative of the given curve, the dy dx, and I need to find out when that is equal to 0. All right, so let's go ahead and take the derivative of this curve. So that would be 2x plus 8y dy dx, is equal to 0 plus, okay, 2xy, I'm going to hold the 2, and I'm going to do the derivative of x times y, which would be x dy dx plus y times 1, which I don't need. All right, so let me clean this up here a little bit. So I have 2x plus 8y dy dx is equal to 2x dy dx plus 2y. Okay, so I'm going to bring my dy dx terms to the left-hand side, and I'm also going to go ahead and factor out that dy dx while I do it. So dy dx, and then I would have 8y, and then I'm going to subtract the 2x, so minus 2x, is equal to, on the right-hand side, I'm going to collect my non-dy dx terms, so I have the 2y already there, and I'm going to subtract over 2x. All right, so dy dx is equal to 2y minus 2x all over 8y minus 2x, which of course everything can be divided by a 2, so I'm going to do that, y minus x over 4y minus x. Okay, so now remember, the next thing I need to do is set that slope. The whole thing I was doing was finding the slope so that I could set it equal to 0. My slope has to equal 0. Okay, so I'm going to go ahead and take this slope, this y minus x over 4y minus x, and set it equal to 0 over 1. Which of course that would mean I would cross multiply and I would just end up with y minus x is equal to 0 or y is equal to x. Alright, so now if you remember, alright, the whole goal here was to find the points at which there was a horizontal tangent line. So to find my points from my original curve, I have to go back to the original equation of the original curve. Okay, went back and grabbed it and wrote it down here. And so now what we're going to do is replace all of the y's with x and solve it from there. So, or you could replace all the x's with y's. It doesn't really matter. Okay. So I'm going to go ahead and have x squared plus 4x squared is equal to 12 times x plus, 2x times x, or x squared. All right, so this would be 5x squared is equal to 12 plus 2x squared. Bring that over, so I get 3x squared is equal to 12. So x squared is equal to 4. So x is going to equal plus or minus 2. Okay, so these are my x values. So I have 2 comma something and negative 2 comma something. Well, right here I was told that y is equal to x when the slope is equal to 0. And so I know that my y value is also going to be, because y equals x, 2 and negative 2. All right, so I have my 2 points now for which the horizontal, that forms a horizontal tangent line at this given graph. Okay, the second part of this question says, at each of these points, which of course we just found those points to be 2, 2, and negative 2, negative 2, determine, if possible, whether the curve has a local min or a local max. All right, so there's our points. So we have to do 2 things to determine whether or not it's a local min or a local max. All right, so first of all, if I were to do this, as soon as I see those words local min or local max, I want to try to use the first derivative. So once again, if you remember, what is our first derivative? Okay, dy dx is equal to y minus x over 4y minus x from the first question. Okay, from the first part of this question. So we have that. Now notice again that your derivative, your first derivative, is dependent upon both x and y. So I cannot use the first derivative test because I don't have a y value to plug in. Therefore, I'm going to go through the second derivative test. So first of all, I want to take my point and I want to make sure that the slope is 0 at that point. Just kind of verifying the work that I did on the part 1. So dy dx at the point 2, 2 equals. So that would be 2 minus 2 over 4 times 2 minus 2. So of course this is 0 over 6, which is 0. Okay, so that's the first part of the test. The second part of the test is to determine if my second derivative is positive or negative, which means I need to take the derivative of my given slope. So d2y over dx squared is equal to, all right, so clearly this is a quotient, so I'm going to use the quotient rule. Low, 4y minus x, derivative of the top here would be dy dx minus 1. So low d high minus high, y minus x. D low would be 4 dy dx minus 1. All over 4y minus x squared. Okay, so that looks kind of ugly, but I'm just going to take that, rather than spending a bunch of time cleaning it up, I'm going to go ahead and now plug in my point 2, 2 into this and see what I get. All right, so I have 4 times 2, which would be 8, minus 2, which is 2. All right, times. Now when I get to the dy dx, again, I've already found the dy dx at 2, 2. I've already found the first derivative at 2, 2 right here, and I know that it's 0. So that's what's going in for this. So it's 0 minus 1 minus 2 minus 2 times 4 times, again, there's that 0, dy dx is 0, minus 1. All over 4 times 2 is 8, minus 2 cubed. Okay, so I get 6 times negative 1 here would be negative 6. Minus 2 is 0. 0 times anything is going to be 0. So that just goes away. All over 8 minus 2 is 6 cubed. Okay, regardless of cleaning it up any further, I can tell that that very much is less than 0. Okay, so I now know that I have a second derivative that's less than 0, which means I have a graph that is concave down, which means that I have a maximum at 2, 2. So I can go ahead and make that conclusion. 2, 2 is a relative max. And why? Well, two conclusions. First of all, the first derivative at 2 was equal to 0, and the second derivative at 2 was less than 0. Okay, so now we have a second point to check. All right, and our second point, of course, was negative 2, negative 2. And again, we're checking with this slope, dy dx, was y minus x over 4y minus x. So again, the same two checks. First of all, let's go ahead and put in and evaluate dy dx at the point negative 2, negative 2. So it's going to be negative 2 minus negative 2 over negative 8 minus a negative 2. So it's again going to be 0 over, let's see, negative 8 plus 2 would be negative 6. Either way, you get 0. All right, so the first derivative is equal to 0. So now we move on to the second part of the check. Does the second derivative positive or negative? All right, we already evaluated the second derivative up here. So let's go ahead and grab that. Okay, so I took the second derivative from up above and I copied it and pasted it down here. So you want to recopy that down, all right? And now we have to evaluate the second derivative. So d2y over dx squared at negative 2, negative 2. And we have to see what happens here, all right? So we're plugging in negative 2 and negative 2 for x and y. And, of course, we know our dy dx is 0 from right here. All right, so go ahead and plug it in here. We get negative 8 minus negative 2 times 0 minus 1 minus negative 2 minus negative 2. 4 times 0 would be 0 minus 1. All over 4 times negative 2 is negative 8 minus negative 2 squared. All right, so let's go ahead and evaluate this and see what we get. So negative 8 minus negative 2 would be a negative 6 times negative 1, though, is going to be a positive 6. All right, again, we have negative 2 minus negative 2 here, which is going to be 0. So this whole thing is going to be gone. All over negative 8 minus negative 2 would be negative 6, but then we're squaring it, so we're going to get a positive number on the bottom. So we end up with a second derivative that is greater than 0, telling us that our function, our curve, is concave up at that point. If it is concave up and the first derivative is equal to 0, then we know we have a relative min. Okay, so our final conclusion is that we have that negative 2 is a relative min, and the reason why would be because f prime of negative 2 was equal to 0, and the second derivative at negative 2 was greater than 0. Okay, guys, that's it for today. I hope you took good notes, and I look forward to seeing you in class next time.